Okay, thanks a lot for having me here. It's a pity I had to miss a large part of the conference, and similarly to Son, I also missed a large part of QCD development. Actually, more than for me, I started thinking about it about 10 years ago, so I had a lot to catch up. This talk will be about understanding spectrum of QCD, and by QCD, I mostly mean here young males, actually. Well, not only, you'll see. And most part of the talk will be, no, I already think did something wrong. It will be about 3D young males, although much of what I say applies also to 4D, and I'll say a few words about that. And this is based on the work in progress with Gabriel Coma, Guzman, Hernandez, Scheffler, Sasha Moni, and Sharzad Zari, and it's continuation of earlier work which we were doing. And there are a related line of research pursued by Kobison and Shine, and also by Simeon Hellerman. So, well, the main goal for this line of research is to obtain a systematic analytic description of the global spectrum, or at least part of the global spectrum, hopefully a large part of the global spectrum. Well, and also light quark mesons. Well, because for heavy quark mesons, part of the spectrum can be approximated basically by Coulomb interactions of quarkonia. But here I'm thinking about really kind of stringy part of QCD. And the only approach I'm aware of is to achieve this is to use combination of large NC and large J expansion. And so basically the idea is that, well, in this regime of large N QCD, large J states can be, on the leading Regge trajectory, can be described by folded rotating rod solution. And the string, due to large N suppression, wouldn't be breaking, so I can really consider long large J regime. And then one can obtain a spectrum of perturbations around this semi-classical solution. That way obtain a bunch of excited states from dotted trajectories, and that should give a part of the global spectra. So, as I say, much of the talk will be about 3D young males for main reason because it's simpler, and their situation is more clear. And but let me show you, to illustrate you that there is some data. So so first of all, this is, to my knowledge, the most precise data on the spectrum of D equals 3. Well, for practical purposes, this is SU infinity young males. So in practice, I think the measurements were done up to SU 16 and interpolated up to NC equal to infinity. But in reality, the difference between NC equals 3 and NC equals 16 for most of the states actually is a level of 10% maybe at most. So this restriction of to large NC, at least for purpose of this talk, it doesn't seem to be that significant. So what's shown here is a spectrum of global masses, and the horizontal axis is their spins. Well, however, because these are lattice measurements, lattice breaks spin like continuous rotations to discrete rotations. And actually, the spins shown on this plot, they are Z4 spins rather than O2 spins. And the states which were put in circles here, these are states for which there were extra work has been done, and there were claims that they actually spins correspond to what they're shown here. So that, for instance, well, these are singlets, for instance. For them, it's simpler because, the high spin states, they come in doublets. That's why it also D equals 3 is a little bit tricky, because in higher dimensions, 4 dimensions, there is larger multiplicity of spin states here. All non-zero spins, they're doublets, so it's hard to distinguish them. But anyway, so for these states, at least at the time when this paper were published, for circle states, there was claims that the spins were actually determined. And there is another piece of data, and I'll explain later what was motivation to do that. But later we performed simulation also with Mike Tepper and with PhD student at NYU the goal of that simulations were specifically to measure spins. So the results here, they are less precise if you compare these two plots. I didn't put them all together. They are, so they don't quite agree for the actual values of the masses. There are discrepancies. But the goal here was really to perform precise spin determinations. And so there is, and for the structural kind of structure of the spectrum, that plot is very useful. And the main message for the moment is that, well, first of all, there are many states being measured, but also clearly, well, it's not just random mass. One sees some structure in the spectrum, right? So I'll explain later in more detail, but roughly speaking, the color coding here, so the states which correspond to the same color, that would be states which in string theory language you would call string states at the same level. And in critical strings, for instance, they would be exactly degenerate. Well, and we see that for Young Mills, for 3D Young Mills, there is not exact degeneracy, but still there is a clear separation between different levels, and there are splittings. And the hope is that by doing this large J expansion, one should be able to calculate the splittings at least for large part of the spectrum. That's what we're trying to achieve. And actually, well, that's to some extent that's their most modest hope. As I'll explain later, something more interesting going on. And actually, there is a hope even to understand the whole spectrum, even though a priori it looks like there is no reason to expect that that should be possible. This perturbative expansion I'm talking about, that kind of guaranteed to work only in the vicinity of leading Regge trajectory. So for states kind of at large J and not too excited. But something more interesting going on, and I'll explain it later. So that's what we're trying to do. And well, naively, well, it looks somewhat straightforward. So for instance, well, these were Glueballs, so they were closed strings. But instead, one is thinking about now theory with fundamental quarks and light quark mesons, then the leading Regge trajectory would be described by this rotating rod solution. Well, and similarly, so that's a classical solution of just Nambu-Goth action. And similarly for closed strings that's relevant for Glueballs, the leading Regge trajectory would be described by this folded string. So basically, it's twice the same solution. And then you may calculate for this solution, you may evaluate the value of J and value of energy. That gives, of course, the classical linear Regge slope. And in particular, large J from this expression, so omega here is the rotation frequency. So large J corresponds to small omega. So these strings, large J strings, they're long, not surprisingly, and also they're slowly rotating. So one expects that those should have good semi-classical behavior. And then one would like to consider small perturbations around these semi-classical configurations and describe excited Glueballs. So that's kind of the program here. However, there is a subtlety, and namely the subtlety is related to this endpoints singularities. It's more obvious for closed strings. For closed strings, clearly, this solution, there is a fold at the endpoint, so it's obvious that there is a singularity. But in fact, there is also singularity with Neumann boundary conditions. There is also singularity for open strings. That's something which kind of initially was a bit surprising to me. That's the first thing you see almost in any string theory textbook, and somehow in kind of critical string theory, without like noticing this, like from the very first page, one resolves certain singularity, which is true singularity from the effective field theory viewpoint. And to see that, so let's look at just open string. So what I'm showing here, this is the induced metric on the volt sheet. And with Neumann boundary condition sigma, which is a coordinate along the string, it runs from -1 to +1. So just by staring at this induced metric, first of all, one notices that the endpoint of a string with respect to observer sitting at the center of rotating string, it has kind of infinite redshift, so it's a little bit like black hole horizon, but it's not a horizon. It's actual curvature singularity. One can calculate. So here I calculated the square of the extrinsic curvature, but one can also calculate the induced just scalar curvature on the wall sheet. And all these curvature invariants, they all blow up at the endpoints. So if one thinks about this long string configuration as a kind of effective field theoretic object, then there is naked singularity at the endpoint, and kind of one way to see what it leads to is because this is a solution of Nambu-Goto action, but kind of in the systematic, what we're trying to do, we're trying to use kind of effective low energy theory based on Nambu-Goto action plus high-dimensional corrections to Nambu-Goto action. And if you look at some high-dimensional operator, which you expect to be present in the bulk, and naively, by naive power counting, you expect it to be suppressed, then by evaluating, by saying that, well, let's cut off the singularity at the place where curvature becomes of order the string tension, right? That's the UV scale of this AFT, and that corresponds to this redshift factor of this order. So if one cuts off the corresponding integral at that scale, one finds that all high-dimensional operators, which you can write in the bulk action, they all contribute at the same order. So as a result of the presence of this singularity, kind of naive power counting breaks down. And that's a technical subtlety which one needs to deal with in order to treat this system as low energy effective field theory. And that's actually the main content on what we're doing in this ongoing paper. But the idea is that to restore effective field theory power counting, essentially one needs to absorb these divergences into boundary counter terms, but that's not surprising from this picture. That matches what I was showing on the previous slide. And one qualitative consequence of that this becomes a two-scale system. So naively, there is a only cutoff. Like in the bulk, there is a cutoff scale which is set by the tension of a string. However, because of this redshift effect, this bulk cutoff at the endpoint, it gets redshifted by this redshift factor shown on the previous slide. And so the cutoff at the boundary is much lower. And that's already provides intuition. So if one way to remove the singularity, for instance, replace, instead of considering massless quarks, one can add, consider open string with a massive quark at the end. And when one does that, there is no singularity anymore. But of course, when the quark mass approaches the string scale, still the power counting breaks down. But working, say, in the heavy quark mass regime, one recovers like the corrections to the linear Regge behavior of this kind, which involve this funny fractional powers of J. And that organization of the perturbative expansion is immediately follows from kind of this picture. So the point is that, again, these corrections are suppressed by the cutoff at the boundary, at the endpoint, which is redshifted with respect to cutoff in the middle by this redshift factor. So while that's kind of the technical issues one need to deal with, but at the end of the day, and also actually Simeon Hellerman had similar proposal. So at the end of the day, it looks doable. So in practice, this leads to somewhat unconventional boundary action. So essentially, one writes local operators, but one uses so one treats the system as perturbation around Neumann boundary condition. But for Neumann boundary condition, the induced metric on the boundary, which would not normally put in this expression, it becomes singular. So instead, one uses kind of this metric-like object, which involves second derivatives of the target space coordinates. So it's somewhat unconventional, but it looks like it provides a way to restore power counting, and one can live with this. And so at the moment we're working out like consequence of leading order splittings in this power counting scheme. So I don't have the results yet, so stay tuned for that. But for now, oops, I did something. Okay, yeah. So what I will discuss now, I'll discuss in some more details kind of the global quantum numbers, the full spectrum. And actually there was...
Sorry, for some reason Zoom stopped the screen share. Was this the slide?
Yeah, that was the next slide, yeah. Yeah, thank you. So there was an interesting puzzle about the quantum numbers of well, the overall structure of the spectrum which one finds in this approach. That's something which I already mentioned in the beginning. But there is an interesting puzzle which I will try to explain now. And I think it is resolved, and again, in a somewhat interesting way, at least to me. Basically, I learned something new about harmonic oscillator on the way. So I'll share this. Well, probably for many of you, it won't be new knowledge, but anyway. Namely, what happens in 3D Young-Mills, so a priori, so as I said, this approach would allow to calculate the spectrum of low line states close to the rigid trajectory. But initially, we were trying to be more ambitious, and actually, we used it, we came up with an ansatz for all global quantum numbers. So the claim here was really at the kind of working at the leading order in this effective field theory. At the time, we also didn't know yet how to properly calculate corrections, so we had to work at the leading order. So at the leading order, one gets this exact degeneracy level by level. And I'll explain it in more detail, but there was a prescription which was not exactly effective field theory calculation. It was a little bit more, but it was a certain ansatz whose goal was to try to describe all global quantum states, including ones which are far from leading rigid trajectories. And so what I mean by quantum numbers here, I mean, well, it's 3D Young-Mills, so there is spin, parity, and charge conjugation. Well, and really, parity only is a meaningful quantum number for scalars, because states with non-zero spin, they come in pairs of opposite parity. And basically, well, these ansatz, so the name here stands for, this ASA stands for axionic string ansatz, and that refers to something which happens in four-dimensional Young-Mills. So I'll maybe say a few words later on. But it was inspired by thinking in a unified way about 3D and 4D Young-Mills. And in 3D Young-Mills, it's roughly speaking reduces to saying that 3D confining strings, that's the bullshit theory, in some sense in the equivalence class of just Nambu-Gote theory. And I'll say a few more words what I mean when I say that. And motivation for this ansatz, initially was inspired by the following two observations. So first of all, well, in general, in any number of dimensions, if you consider long string, so clearly to define kind of spectrum of all Glueballs, one need to specify what theory lives on the voltsheet of that confining string. For low line states, we can think just of Nambu-Gote, but in principle, one expects to find additional massive states. Now, there are two observations which makes D equals 3 situation special. So first of all, in any number of dimensions, the voltsheet theory on the long string at the classical level, it's integrable. And then at the quantum level, due to one loop effects, if you consider scattering on the long string, there is particle production on the voltsheet, which is proportional to D minus 26. So that's long string way of thinking what critical dimension is about. However, for at d equals 3, d equals 3 is special. At d equals 3, there is actually a model with a single degree of freedom where integrability is preserved. So it's a little bit like d equal 26 from the long string perspective. So that's one observation. So one need, and another observation, just looking at the lattice data for the spectrum of confining strings, for d equals 3, they don't show any signs of additional massive states. So it's different at d equals 4, but for d equals 3, so there are kind of plots like this, which were, again, obtained by, so left-hand side is a plot obtained by, again, Mike Tepper by measuring excitations of long strings wrapped around a compact circle. And the right-hand side is a scattering phase shift extracted essentially using Lusher formulas using from this data, and one finds that there is a growing amplitude, growing phase shift, but there is no sign of any kind of massive resonance up to pretty high values of the momenta on the world sheet. So it looks like the only degree of freedom which is present there is this massless boson, which corresponds to translational mode on the string. And kind of based on these two assumptions, well, based on these two motivations, we came up with the ansatz, which I'll describe first, and then I'll just give you the result and try to convince you that the result is interesting to look at it in more detail. So back in that 2016 paper, we came up with the ansatz for Glueballs spin content. So again, it's a leading approximation. So the states are organized by level, and level by level is a leading approximation. There is exact degeneracy, which hopefully later we'll be able to calculate splittings between these degenerate states. But kind of the prediction for spin content of level by level is shown here. And kind of to see how good this prediction is, let's compare with the data which I was showing to you before. So the data which were available at the time, this is the data which I refer to on my second slide. So it worked. If you look at this table, it kind of worked for n equals 0, n equals 1, and n equals 2 states in levels. But it shouldn't be really counted as a prediction because it was more like a postdiction. So we were coming up with our ansatz. It was more or less simultaneously when this paper were coming out. So we knew this result. And actually, for n equals 3 states, there was some tension, namely the circle states here. There is spin 1. If you see there is one spin 1 state, it's three spin 3 states. And if you look at our ansatz, then we're expecting there should be 2 spin 1 and 2 spin 3. And there is very general argument, at least in following our logic, why odd spin states should come with opposite parity, opposite C parity. So there was a clear tension. So that was a situation back when this prediction came out. So there was agreement for low-lying states, and there was some tension. So that was the motivation for obtaining this other set of lattice data, which I showed to you, namely to perform dedicated measurements of spin states of the glue ball. And basically, the idea is that you construct, there is no exact O2 rotation on a lattice, but you can, if the lattice is large enough, you can construct operators which are approximate eigenstates of O2 rotations, and that way to distinguish the different values of J. And that requires quite large lattice, so that's why we couldn't go to large NC. And also the mass determination was not that precise, but that resulted in this plot, which is shown here. And so first of all, this problem in J equal 1 and J equal 3 sector turned out to be resolved. So there was some spin misidentification in earlier data. Well, and moreover, so if one looks now at n equals 3 states, so there is this green states. And almost at all values of spin, they're quite well separated from the states which we here attribute to n equals 4 level, apart from maybe n equals 0 or J equals 0, where there are lots of states and broadening becomes quite large. So here it's hard to say something like it's a little bit up to us how to divide the states. But for all other values of J, there is a clear separation between levels. And these states, they match what was predicted back here. And this is in total 25 states. So I think that's looks interesting enough to take this prediction seriously and to understand what's going on. And in principle, while there is like 64 states at n equal 4 level, again, there is no, well, there also data becomes worse, but it's fair to say there is no place where there is clear tension between the prediction for the states and what is being observed on the lattice. So at face value, well, actually, it looks almost too good. So because basically it says that all these global states, you can think about them as kind of some specific wiggling configurations of just single bosonic states. And it goes up to pretty heavy mass. And so one expects maybe to find some non-perturbative states in the spectrum. But anyway, that's the current situation. So, well, and let me now tell you a bit. So the puzzle, which kind of I want to explain you how it got resolved, is related now to the calculations which went into this prediction. So let me, hopefully I managed to convince you that this prediction looks sufficiently successful to take a look at it more carefully. So what went in our ansatz? So there were several statements. So first of all, we said, well, it was motivated by what happens for critical strings. So we're trying to predict the spectrum of Glueballs, which are closed strings. And in critical strings, the Hilbert space of closed string states is given as a sum over levels. So there is level matching condition. There is sum over levels. And at each level, one finds that states in the tensor product of left movers and right movers. Well, and actually, there is more to that. And in critical string theory, and that we'll use later, the critical string theory is these Hilbert spaces themselves correspond to Hilbert spaces of open strings. But as a very first step, one can even not make this assumption, but just say, well, we expect to find the structure of Hilbert space which has this form. And the charge conjugation, it just corresponds to changing the orientation of a string. So it replaces left movers and right movers. Well, and to me, this looks almost like a definition of what you mean by the one-dimensional kind of like by string object without any massive states. If there are massive states, in addition to left and right movers, you can add these massive states on the volt sheet, so the structure will be more rich. But if all what you have is just massless excitations, that makes sense. And the fact that the level matching condition, of course, it's not peculiarity of just critical strings. It's just the statement that momentum along the string volt sheet is a gauge generator. It corresponds to diffs on the volt sheet. So if the string doesn't wind around some non-trivial circle, if you are in a sector with no windings, then you should only have the level matching condition should hold. Well, and already this simple ansatz, it already has some power. Namely, it tells, first of all, it predicts that level by level you expect to find multiplicities which are integer squares. And also, it controls what kind of representations you can obtain. So this is kind of simple multiplication table for O2 reps. And in particular, this fact which I told you before, that odd spin states always appear in powers of opposite parity. You can see here. So the odd spin states here, they can only come, well, either on this line or on this line, and they always come with powers in pairs of opposite C parity. So it was really very hard to get around that. That was the reason why we were so confident to start with that there was some problem with lattice data for those spin 1 and spin 3 states. So already here, one gets, in principle, some set of non-trivial constraints on the global spectra. However, we made another step which relates to what I was describing in the beginning. Namely, we said, well, let's assume that just like in the in critical string theory, these left and right mover states, that Hilbert spaces which you need to tensor square, they correspond to Hilbert space of open strings. And the way we determined these open strings Hilbert space is using large J perturbation theory. So we took rotating rod solution, not directly for closed string, but for open strings, and considered small perturbations around, constructed small perturbations around that solution, and that allowed us to construct open string Hilbert space at large J. Well, for now I'll skip details, but basically one works with Polyakov action. It's in 3 dimensions, but so it's non-critical theory. But at leading order, the anomaly is quantum effect, so one can work really with just Polyakov action and solve Virasoro constraints. And at the end, one gets a spectrum which looks like for each J, one finds a infinite tower of oscillators, and where the first one is skipped, and because that one corresponds to change in the state along the first Regge trajectory, and so that's kind of proceeding this way. One obtains this plot. So that's kind of what we call semi-classical spin content for open strings. Namely, at each J, it's a prediction for this open string spectrum as a function of J, multiplicities of states, and each column here is the same. It's just large J answer taken all the way down to J equal to 0. And one can compare this spectrum of states with what one gets by doing light cone quantization of a string. Well, famously, first of all, in light cone quantization, what I mean here by light cone quantization actually is the following. So one works at general D, and one gets the generation functional for representations of different of OD minus 2. And famously, they combine for all states, apart from those on the first level, they combine into representations of OD minus 1. And then I take this answer at D equals 3, and I get this multiplicity. So there is this minus 1 here, which corresponds to the fact that for critical, that's kind of the reason why critical bosonic strings have tachyon. It's not the tachyon itself is a problem, is that at the first level you have meta content of a massless particle. So it's really a problem about Higgs mechanism. So here you don't get multiplets corresponding to OD minus 1 little group, but only OD minus 2 little group. And for all other levels, one gets, somewhat miraculously, in any number of dimensions, one gets this OD minus 2 multiplets combined into OD minus 1. So what's shown here, the red numbers, that's where calculation done this way, where it agrees with what we did. And basically, it illustrates the statement that close to leading Regge trajectory, because this kind of problem of the string lives in non-critical dimension, and the light cone quantization is not completely consistent. This problem is a quantum effect, so it should manifest itself for highly excited states. So close to leading Regge trajectory, where effective field theory guaranteed to work, kind of different ways of doing calculation, they should all agree. And that's what one finds here. So there is this red region where a result obtained by light cone quantization, which is not the right procedure, and obtained by just naive extrapolation from large J to all values of J, which is, again, a priori is not guaranteed to work. So these two prescriptions, of course, they agree close to leading Regge trajectory. But then what we did, we kind of bravely closed our eyes and just took this spectrum, which obtained a large J, but extrapolated to all values of J, put it in the tensor squared, and that's where prediction for closed string spectrum, for Glueballs spectrum came from. well, and somewhat miraculously, it works as we saw. It works for first 4 levels. In particular, it works really for j equals 0 Glueballs. So that's where it's supposed to fail. Well, actually, when we're doing it, we were not appreciating that that it's that non-trivial. We kind of thought that it's guaranteed to work. So it looks like we're somewhat lucky. But it's natural to ask the following question. So here I followed this somewhat awkward procedure. Instead of directly working with effective closed strings, which is consistent effective field theory way of doing it, thinking about leading edge trajectory as this folded closed string, and quantize perturbations around closed effective closed string, obviously closed folded string solution. I considered open strings, first constructed open string Hilbert space and then squared that. So that's not effective field theory procedure, and that worked. And to be honest, when we were doing it, we thought it's just technically simple. It should give the same result, but that's wrong. So in this paper, instead we did what I just said. So we calculated, took folded closed effective string and looked at the perturbations around that one. Well, and again, I'll skip the details, but the bottom line is that the resulting spectrum, proceeding this way, one gets yet another spectrum. And this spectrum, again, so here I'm comparing this spectrum to this, oops, sorry. Not to light cone spectrum, but to the spectrum obtained in previous way. And they again agree close to the rigid trajectory. So kind of in the regime where effective field theory guaranteed to work, of course, it's not a surprise. You always get in the same states. But these 3 different procedures, they predict the same states close to leading rigid trajectory, but predict different set of states highly above leading rigid trajectory. And this can be summarized in the following way. So kind of in the light cone prescription, so you calculate closed string light cone spectrum by taking the square of open string light cone spectrum, and you get less states than by taking kind of this open string lat j quantization and squaring that. And instead, if you take closed string lat j quantization directly, and sorry, there should be no square here. So that shouldn't be squared. So what stands on the right here is just doing directly a closed string effective field theory quantization. So that produces even larger number of states. And somehow it looks with the data, the prescription which works is the one in the middle by taking lat j expansion for open strings and squaring them. And that's something which one wants to understand. We don't have full understanding why it works, but zeroes out the question kind of where this disagreement between these different prescriptions is coming from. Because, well, of course, as I said, all spectra agree in the FT regime. And then I say, OK, when you go to excited states, there will be corrections. So one expects get different results. But actually, at least as the value of masses go, the values of mass squares are all the same. Well, because the splittings, it's again related to the fact that this consistency of light cone calculation, it's a quantum effect. And at the classical level, this is an integrable theory. So even though kind of the way we organized our calculation in effective field theory, we were kind of doing perturbative calculation, but this perturbative calculation was guaranteed to produce at the leading order the correct result. So it's not clear. Technically, if you're trying to push it to higher orders, well, you see it as a result of very non-trivial constellations that indeed you get the corrections cancel. Classical nonlinearities, they reproduce exactly the light cone spectrum, but it's technically not obvious at all. But anyway, so the situation is there are 3 calculations which produce the same values of the masses, but they produce different multiplicities. And kind of it was somewhat puzzling how to understand these differences. And Well, what we understood now that it all boils down to the simple calculation which one can do with. Well, actually, one can do it with a single harmonic oscillator, but it's better to talk about two harmonic oscillators because that captures better the situation, what happens here. It has a better analogy. Namely, kind of let's consider kind of analog of this EFT quantization for a system of two harmonic oscillators. So here, what I wrote, this is an action, well, written kind of in first order formalism, but it's just familiar action for two harmonic oscillators with frequencies little omega and capital omega, and capital omega is larger than little omega. And I want to count states, and so here with as a function of j, which is this particular combination of excitation numbers for this harmonic oscillator, so that's kind of analog of j in the full string picture. And kind of what you have in mind, what you should be thinking about, kind of this little a is like the lowest frequency oscillator for a string, which forms leading edge trajectory, and then this capital A is one of the excited oscillators. Well, and of course, well, these are harmonic oscillators, so we know how to quantize harmonic oscillator. We know how to count states. So there is leading edge trajectory because little omega is smaller than capital omega. There's leading edge trajectory which is built of these states, J0. And then there are excitations when you remove one of the little a and add one of the capital A so that you don't change the total J. And there is finite number of them. You can go all the way from J0 to 0J. And so you get J times little omega, the energy of the states on the leading edge trajectory, and J times capital omega for the highest energy state. So this is the answer, which is clearly, which describes what happens here. But however, let's try to mimic the procedure which we were doing when we were applying this effective field spherical quantization. Namely, let's now take a background and let's quantize around this background. Naively, it shouldn't change anything because, well, harmonic oscillator is a linear system. So by taking non-trivial background and quantizing around non-trivial background, nothing should change. But here, what one gets, kind of, well, the background here corresponds just kind of keeping, oops, sorry, I did, no. By this chi and delta and alpha the excitations, the background corresponds just having J0, and like that's analog of rotating string background in this two oscillator example. And kind of this parameterization of excitation, this is kind of the natural set of parameterization when you do this effective field theory calculation around rotating background. These are natural modes. So delta is kind of a Goldstone mode associated with unbroken linear combinations of unbroken time translations and rotations, which is preserved by rotating string. And so these are natural variables in which one is working in this effective field theory calculation. And if one does it, one obtains kind of this action for in terms of these variables. So it amounts by doing canonical transformation from kind of initial oscillator basis to the basis delta and j, the two canonically conjugate variable. And then there is kind of co-moving oscillator alpha, and its frequency is shifted so the, well, so here this alpha is the same as beta. Or this beta is the same as alpha. So so its frequency is kind of one gets state labeled by j and delta, and at each j there is infinite tower of states whose frequency is shifted by, it's equal to the difference between two frequencies. So it's a frequency is kind of co-rotating frame. Well, and that's different answer from what one obtained here. So namely, what this procedure is missing. This procedure is missing the fact that there is the two spectra agree for low line states, but they disagree for sufficiently excited states, because this procedure, roughly speaking, it's effective field theory procedure. It's missing that at some point kind of there was a background and you exhausted all the excitations on the background. And doing this effective field theory calculation, you don't notice it. Well, or more precisely, like in this canonical, in this two harmonic oscillator language. So what you are doing, you are trying to do this canonical change of variables between these variables and these variables. But this change of this canonical transformation is not well defined globally. Namely, well, the phase space for two oscillators is R4, and here we have R3 crosses 1, whereas 1 is this phase. Well, and actually, both of these systems which are written here, this system and just two harmonic oscillators, they're both well-to-do quantum systems. They're just different quantum systems. So locally, there is a canonical transformation between them, but globally, the structure of the phase space is different, and that's why one gets a different set of quantum numbers. So of course, in this, if our initial problem was really to talk about the spectrum of two harmonic oscillators, then that procedure is correct. That gives the correct answer, and doing this canonical transformation is not a legitimate thing to do. However, in principle, this quantum system is also well to do on its own, and it can exist. And coming back to strings, so by actually there, and one can now, so remember we had these three situations, so one can follow kind of what's going on. So at the end of the day, yeah, all these differences between spectra, which one obtains just doing light cone quantization or open string squared, or directly with closed strings, it's related to these kind of choices. One makes different choices of canonical variables, which all locally agree around the classical solution, but globally they describe in different phase spaces, and they produce. That's why they produce globally different spectra. And it looks, just looking from the data, that in that case the procedure which gives the correct answer is not kind of to work in a space of harmonic oscillators, but it's kind of in between. For some variables, one need to work in angular coordinates. Well, and a posteriori, it's not that surprising, because if you remember light cone quantization, its starting point is a very singular string configuration, a string of like zero length. So those harmonic oscillators, which one finds in the light cone quantization, they're not guaranteed kind of to exist truly, because they correspond to a singular background x plus equal to tau, and string is shrunk to 0. So in some way, it is more surprising that that procedure still correctly works for critical strings and produces correct spectrum there, even though it corresponds to quantizing around singular background. On the other hand, for the purpose of QCD strings, and we don't fully understand yet why it is kind of that prescription which we have, where when one takes open string and squares it, why that prescription actually is the correct one as opposed just to doing closed strings. But quantizing around closed strings and going all the way, like if T quantization about closed strings, it doesn't even reproduce correctly the tensor square structure. So somehow, but it all has to do with kind of non-trivial manifestation of this anomaly, which is like present at d not equal 26. So here it manifests itself in, one need to correctly understand the phase space structure of this string excitations. And I should say, well, there is, so if you remember kind of the string theory textbooks, so the usual Virasoro anomaly, it appears in any number of dimensions. It appears in the anomaly of between commutators j plus I and j plus j. So the Poincare algebra doesn't work in light cone, but it vanishes at d equals 3. So d equals 3 is special. So so very naively, one may try to say that at d equals 3 anomaly disappears. But I think it's more correctly to say that this anomaly really manifests itself as a kind of global anomaly, which to see its structure, one should kind of look more correct, fully at the structure of the phase space. And it's related to the argument which I had this footnote here. So when actually if one directly does quantization of d equals 3, light cone quantization d equals 3, as was noticed by Mazenchescu and Townsend, even though the Poincare algebra works out, one finds that the states necessarily involve, if one calculates helicity of resultant states, one always gets some irrational anions, which is another way to say that the series anomaly. You started with a classical theory, which is invariant under Poincare, and ended up getting states which in representations of infinite cover. So you change the group. So somehow it's all, I think, related to kind of this global structure of the anomaly for d equals 3. And I think it's interesting to understand it in more detail. But to conclude, let me just give one last comment. So in 4D, in principle, many of what we did is possible to do in 4D. In particular, in 4D, like the low-lying states we should be able to capture that. And actually in 4D, well, it's more complicated situation because they're there from lattice data. It's known that there is additional massive state, which is a massive kind of pseudo-scalar state on the string worldsheet, which we called a worldsheet axion. And there actually, because of that, it's also interesting to look at the to look at the open strings, because that's something which where one can get like Glueballs, of course, also interesting, but still there are kind of no direct experimental observation of gluons to the best of my knowledge. But for open strings, there is a prediction which we're working out now, is that in detail, that if you have Regge trajectory of some meson, there will be additional Regge trajectories obtained by adding this massive excitation on the worldsheet. And this effective field theory technique allows to predict this dot Regge trajectory, which would be predictions for specific exotic hadrons. So stay tuned for that calculation, but let me pause here, stop here, and thank you.
I wonder if you've looked at light front holography. There is a large literature on Glueballs in light front holography. So then you get the duality between ADS5 and the light front quantized theory in 3+1 physical space-time. But it has confinement, so it's not this, it's not the simple theory. It really is a confined theory with, and it agrees with the spectroscopy of hadrons, mesons, baryons, tetraquarks, and then it's now being applied by people to the Glueball spectrum.
But so for instance, the d equals 3, does it have prediction for the Glueballs spectrum?
Yeah.
So
yeah.
Does it match the last?
Yeah. There's the papers I've seen, because I didn't do it, is they match well with lattice gauge theory spectroscopy. So,
okay,
so it's another approach, but it also doesn't have any singularities or anything like that. So I think it might be interesting for you.
Yeah, but that singularity, that's a physical property of this configuration.
Yeah. So anyway, so it's based on ADS5 and the special dilaton, which gives confinement.
Okay, that's interesting.